Hello, my name is Gyeongsik Yang, a postdoc at Korea University. I'd like to introduce our paper entitled Prediction of the Resource Consumption of Distributed Deep Learning Systems. This is a joint work with Changyong Shin, Jeunghwan Lee, Yeonho Yoo, and Professor Chuck Yoo. Nowadays, many domains like language, speech, and even for driving are supported by deep learning models. As the deep learning is applied for many much diverse domains, and they strive for higher prediction accuracy, the model subsequently grows larger. As shown in the right graph, the size of the deep learning model has grown exponentially for the past few years. To train such large-scale models, distributed training, or DT, is essential. DT trains a model with multiple GPU nodes called workers. Suppose that there exist n workers. Then each worker replicates the deep learning model structure. To train a model, the training data set is split and delivered to each worker. Then each worker trains the model by forward and backward propagations. This process results in gradients, which are the differences in the parameters that emerge to find the optimal value for the model. The gradients of workers are collected in a parameter server, and parameter server then updates the model parameters. The updated parameters are distributed to workers, and one instance of this process is called as an iteration. The DT then repeats this iteration until the model converges or for a specific number of iterations. In DT, one of the notable challenges is about resource consumption. In particular, we cannot figure out how much resources will be required or how long the training will take before actually running the training. Because the resource consumption is not identified, AI model developers cannot answer important questions directly, which is related to their cost, such as which GPU is suitable, or how many GPUs and workers are needed, and what network speed between workers will be required. The same is true for AI infrastructure engineers, such as GPU cloud operators. For example, like which node to place and execute the requested training jobs, or whether multiple jobs can be run concurrently on the same GPU, and how many GPUs or network resources should be provisioned. To find answers to these questions, we explore whether it is possible to predict the resource consumption that will be required for a model. Before checking, we define how to measure the consumption of each resource. We target 4 major DT resources that have been identified as critical in optimizing DT performance, and they are GPU utilization, GPU memory utilization, network TX throughput, and network RX throughput. The figures below shows GPU utilization, GPU memory utilization, and network TX throughput. The first thing to note is that each resource shows cyclic patterns of burst and idle resource consumption. In each graph, we denote the x-axis as duration and the y-axis as the respective amounts. Then we can define metrics such as burst duration, idle duration, and burst amount. The defined resource consumption metrics highly sensitive on 2 main causes. The first is the task, which we call as the DT workload. The DT workload is identified by the model to be trained, the data set to be fed to the model, and the hyperparameters that change the operations and calculation during the training. The second is the environment wherein training is to be performed, that is the DT setting. DT setting is defined by the type of GPU used for training, the number of workers and PSs, and the network interconnect type. As the 2 factors change the resource consumption highly, prediction should consider the both. However, several studies did not cover the 2 factors. In terms of the DT workload, existing studies only cover a limited set of model layers, such as convolution and fully connected, which means that it is restricted in terms of the DT workload. And also, most studies do not consider diverse DT settings consisted of GPU type, the number of nodes, and the network interconnect types. To solve this problem, we propose triple. Drupal trains a prediction model called the Drupal inspector. The Drupal inspector takes the DT workload itself as its input for prediction. Then the Drupal inspector predicts 12 kinds of features, which are for 3 metrics: burst duration, idle duration, and burst amount, and 4 resources. The first question here is how the Drupal inspector could take the DT workload itself to the prediction model. We explained the design of Drupal to answer to this question. To design Drupal, we look into how DT workloads are trained. DT workloads are implemented using libraries. For example, suppose a workload as described in the table here. The key is that the libraries convert the DT workload into a computational graph. The graph consists of nodes that express operations such as calculations, variables, and constants. Each node also has features such as node type and tensor size. The nodes are connected by edges, and the edges show the execution order between the nodes. Shortly, the graph includes all the details of DT workloads during the training. Based on this observation, we designed Drupal to take a DT workload by a graph. Because a graph is a special type of data structure, in that each graph has various number of nodes and edges, resulting in non-fixed sizes. So machine learning communities have researched a specialized type of model called the graph neural network, or GNN, that can take the graph as its input. GNN takes the graph by matrices for graph structure and node features. The GNN model consists of multiple graph layers, and per node, a graph layer aggregates the features of the neighbor nodes to generate node embedding, which is the representation value for each node. For example, assume a graph of 7 nodes in the below. The neighbor nodes for the node 1 is 2, 3, and 4. Then the first graph layer creates the node embedding for node 1 using the features of the nodes 2, 3, and 4. In the same way, the first layer creates the node embeddings of the other nodes. Then the second graph layer aggregates the created node embeddings from the first layer. For example, from the graph at the bottom right side, the second graph layer aggregates the embeddings of nodes 2, 3, and 4 for the node 1. In the perspective of node 1, the features of the nodes distant from it are in 2 hops aggregated in this time. GNN consists of k number of graph layers, and the graph number k changes upon the nodes of the input graph. So when the input graph has higher number of nodes, the graph layer increases to reflect the features of further hops. And also, up to now, various GNN algorithms have been proposed, and they differ in the method of calculating node embeddings in each graph layer. GNN then creates graph embeddings, which are representation values for each graph. The layer that creates the graph embedding is often called as graph readout layer. For example, the graph readout layer adds, sorts, averages, or pass through another neural network for the node embeddings and create a new graph embedding for a given input graph. Based on this GNN structure, we designed the Drupal inspector as follows. First, we add a GRU layer after each graph layer. A GRU layer is commonly used to prevent loss of information when the number of layers become higher. Also, 3 MLP layers composed of fully connected layers are used to predict the final 12 output features based on the graph embedding values resulted from the graph readout layer. In addition, to select an algorithm for graph layers, we empirically experiment with 4 representative GNN algorithms. And then we use GCN, Graph Convolutional Network, that shows the lowest prediction error. Also, to determine the number of graph layers, we also conduct another experiment. Given M, which is the number of nodes of an input graph, we test various numbers of graph layers. Then M over 2, which shows the lowest median error, is chosen for the graph layers. For the readout layer, we compare the prediction error between 4 methods and select set to set that uses LSTM neural networks for dribble inspector. Next, we explain how to train the designed dribble inspector. For training, a data set is required. But to the best of our knowledge, there are no data sets on the resource consumption of DT. So we developed tools for creating data sets. As the data sets consist of input features and labels, we propose 2 tools called Input Builder and Dribble Puff. To create data set, we train representative image classification and natural language models varying models, data set, and hyperparameters. Please check the details on the Input Builder and Dribble Puff in our paper. So up to now, the dribble inspector is trained to take various DT workloads. Next, we tackle how to predict various DT settings. We consider whether a single dribble inspector can predict the resources required for multiple DT settings. So we compare 2 scenarios where the first scenario is that a single inspector predicts 2 kinds of GPUs, 3100 and 2080 Ti. And the second scenario is that of training 2 inspectors for each GPU. The graph below shows the prediction error between the scenario 1 and 2. The prediction error reduces by up to 43% in scenario 2, where the inspector is trained per DT setting. So we train dribble inspector per DT setting, considering the prediction accuracy. However, the problem is that training inspectors for each DT setting require high training time. Between the 2 scenarios, scenario 2 requires 1.5 times higher time to train 2 models. So to improve the efficiency in training, we use transfer learning. Transfer learning is a training technique to leverage the knowledge of the pre-trained model to the new target model, so that the training time and the dataset size are reduced. In particular, transfer learning reuses well-converged layers and fine-tunes other layers selectively. To choose which layers dribble inspector fine-tunes or reuses, we conduct the following experiments. By changing the sets of layers to fine-tune, we measure the prediction accuracy and training time. Then, by considering both the measured metrics, we fine-tune half of the graph layers and the MLP layers. The remaining layers use the parameters of the pre-trained model. Now, we conduct evaluations for dribble as follows. We use DT workloads similar to those used up to now, and we evaluate dribble using 14 kinds of DT settings with 3 GPU types, up to 10 workers, and 3 different network types. Our DT settings include scenarios using both homogeneous and heterogeneous GPUs. Also for transfer learning, we use the first DT setting of 2 workers using V100 GPUs as the pre-trained model. With these configurations, I will present the prediction accuracy, the effectiveness of transfer learning, and the application scenario of dribble. First, we show how accurate dribble is using the prediction example. Here, we present the results of the 1-parameter server and 3 workers using 2080 Ti GPUs. In the graph shown here, the x-axis is each DT workload, and the y-axis is a metric normalized to the maximum value. The black line is the ground truth label value, and here the red line shows values predicted by dribble. So we believe that dribble shows reasonably accurate predictions. In addition, we show the training time and the prediction accuracy to show the effectiveness of transfer learning. We train dribble inspectors for 14 DT settings, with and without transfer learning. First, transfer learning enormously reduces the training time until the model converges. On average, the training time is reduced by up to 7.3 times. While achieving the great training time improvements, we check whether there is any negative effect on the prediction accuracy. The figure below shows the average prediction errors of 12 alpha features with normalization. By comparing the errors, we observe that the accuracies with TL is quite similar to the ones without TL, which means that the accuracy has not been sacrificed for the benefits of reduced training time. Next, we show an example scenario where Drupal is used. Assume that an AI model developer tries to train a ResNet 56 model. If V100 and 2080 Ti GPUs are the candidates, the developer can use the prediction results of Drupal as follows. Drupal predicts 2080 Ti is 1.3 times more utilized than V100. Also, in terms of the duration, the idle duration is much more shorter in 2080 Ti. So the developer can choose 2080 Ti because it is more utilized than VBAC with lower cost. Second, assume that the developer trains an overfit model with two 2080 Ti GPUs. To decide which batch size to use in training, the developer can compare the prediction results for the 3 different batch sizes. First, Drupal predicts that 2080 Ti is sufficient for all 3 batch sizes, so the developer can choose any batch size from the 3. In terms of the idle and burst duration, the data processed by an iteration increases 4 times when the batch size increases. But the required time per iteration increases only 1.7 times. This means that when the identical epochs are required for training, the training time will be 2.4 times shorter with the highest batch size. So the developer might choose the batch size with 512. Here we have shown simple examples of Drupal, but I believe that Drupal can be used in numerous ways for system optimization or resource provisioning. Okay, here comes the conclusion. To our knowledge, Drupal is the first attempt in using GNN and transfer learning to predict resource consumption of distributed training. While achieving accurate predictions, we reduced the training time of the models up to 7.3 times. We could not cover all the details of Drupal in this talk, so please refer to our paper for other details. Thank you for your attention. I'd be glad to try and answer any questions.